Well, I'm doing this video on work done, and I'm going to introduce you to the concept of work done. The concept of work done, or the meaning of the work done in physics or science, is quite different from our day-to-day understanding of the word work. Right? Let me begin first by writing down the dictionary meaning of the word work done. Right? The Oxford Dictionary mentions work done as an activity involving mental or physical effort in order to achieve a result. Right? This is how the Oxford Dictionary defines work done: activity involving mental or physical effort in order to achieve a result. Right? As far as physics is concerned, first thing is that we do not look at the mental aspect of the work done. For example, if I'm reading a book or if I'm studying for an exam, from a physics perspective, I am not doing any work. Mental work is not considered work in physics. Right? As far as physics is concerned, when we look at work done, we need two things to happen, or two things to exist. One is force, the second is displacement. Right? Okay. F and displacement denoted by S. So if I apply a force on an object, right, and displacement happens, then and only then do we say work is done. Right? If either of them is missing, then we say work is not done. To take an example, if we are pushing a wall, right, let us say this is ground and let us say this is a wall, and I'm applying force on this wall and trying to push this wall, right? It's just an example. Certainly we never do that. And if the wall is not moving at all, the wall is not moving, so there's no displacement, so displacement is zero. In that case, even though we may expend a lot of physical energy, according to physics definition of work done, no work is done because there's no displacement. Right? Similarly, when we do not apply any force, right, we say work is not done. So this is how work done in physics is different from our day-to-day understanding or a layman's understanding of the word work done. Right? So how do we define work done? Right? Let me take an example. Let us say we have an object and we are applying a force on this object, right? And let us say the object moves in this particular direction through displacement F, right, on application of this force. Right? Now, if you look at the definition of the work, then it is something like this. Work is said to be done, right, when a body gets displaced in the direction of the force or one of its components. Okay. This is how work is understood in physics, and this is the more formal definition of the word work done. Work is said to be done when a body gets displaced in the direction of the force or one of its components. So this displacement which is happening in this case, this is an object which is moving along this direction. This displacement has to be in the direction of the force or one of its components. As you can very clearly see, the displacement is not in the direction of the force. But if I look at the components of this particular force, we have discussed in an earlier video that this particular force has two components, Fh and Fv, right? And we can very clearly see that the displacement is in the direction of the horizontal component Fh. Therefore, work done W is given by Fh into S, right? Force into displacement. That's how we define work. But we have to take that force which is in the displacement of the direction, or in other words, we have to take the displacement which is in the direction of the force. So F into H, Fh into S in this case will give me the amount of work done. Right? And as we looked at in the earlier video, Fh is F cos theta into S, where theta is this particular angle. Right? So this is how we get a formula for finding out work done. F cos theta into S, where theta is the angle between the direction of the force and the direction of displacement. Let me write it over here. Theta is angle between the direction of the force and displacement. So this is the very generic definition of work done. W is equal to F cos theta into S. Right. Now let us look at some of the few cases. Right. Let us look at some very simple cases. Right. Let us say we have a case like this wherein the object is this. This is the direction of force. This is the direction of displacement. Right. In this case, theta is equal to 0 because the angle between the direction of force and the direction of displacement is 0. Therefore, W will become equal to, if theta is 0, cos theta will be equal to 1. Therefore, W will be equal to Fs cos theta, F cos theta into S. So cos theta is 1, so Fs. This is case number 1, wherein both have the same direction. Case 2 could be when we have the direction at some particular angle, which we have already discussed, F cos theta into S. We might have a situation where the direction of the force, right, and the direction of displacement, the angle between them is 90. So here theta is equal to 90 degree, right, and cos 90 is 0. Therefore, work will become equal to, now cos theta is 0, so this will become equal to 0. We have such cases. I'll give an example of such case. For example, a man moving up a staircase, for example, right? What is happening is, or a ball being thrown up, right? If this is the ground and a ball is being thrown up, the ball is going up. The direction of the force, the gravitational force is, in fact, that would be a case for when theta is 180 degree. Let us say we have a staircase and, right, a person is moving up with a luggage on his head. Now the luggage displacement is in upward direction, but the gravitational force is acting in the downward direction. Therefore, the work done in this case would be 0 because they are in opposite direction, right? Or a man moving on the I'm doing this video on introduction to work done. What I'm going to do is introduce you to the concept of work done, right? Because the way we understand work in day-to-day life and the layman's understanding of work done and the way work is defined or understood in physics are quite different, right? So the objective of this video is to help you understand how do we define, how do we understand, how do we calculate work done in physics. I'll begin by first talking about the day-to-day understanding of the work done, right? How would a layman understand work? So I'm going to mention the dictionary meaning of the word work done. Right? So the Oxford Dictionary mentions or defines work done as activity involving mental or physical effort in order to achieve a result. But when we look at work done in physics, that's quite different from this understanding of work done, right? Activity involving mental or physical effort in order to achieve a result. Right? As far as physics goes, right, the first difference is that in physics we do not look at mental work, right? For example, if I'm spending a lot of time reading or studying something or preparing for an exam, I'm making a mental effort, I'm doing mental work. But as far as physics is concerned, that is not considered as work done, right? In physics, for work to be considered to be done or for work being done, two things are required. One is force, two required is displacement. Right? These two are necessary. So if I'm applying a force and that force causes displacement of an object, then we say work done. Right? If any one of this is missing, then we say work is not done. Now, we may find it a little bit difficult to understand this concept because, for example, if this is ground and of a room or the floor of a room and let us say this is a wall and I'm applying force on this wall for whatever reasons, the wall does not move. That means there is no displacement happening. So, as far as physics is concerned, work done is 0. But from a layman's perspective, you may say that you have used up or expended a lot of physical energy, right? But the amount of work done still is taken as zero as far as physics is concerned, because there is no displacement. This is how work is understood, right? Or this is the condition under which we consider work as done. Work is said to be done if the object moves or gets displaced, if the object gets displaced in the direction of the force or one of the component of the force. Okay. So this is a necessary condition for work to be considered to be done in physics, that the object needs to get displaced in the direction of the force or one of its components. We'll look at this in more detail, right? And as far as the magnitude of work done is concerned, it is given by force into displacement. And when we look at force, we have to take that force which is in the direction of displacement. So we may not take the actual work, but we may take one of the component of force which is in the direction of displacement. Okay, let us take an example, right? Say for example, this is a ground and there is a box lying on the ground, right? Very simple example. And if I apply a force F on this, because I want to move it along the ground, right? So the box starts moving along the ground. So this is the direction in which the displacement is happening. Now the direction of the force is this, the direction of displacement is this, so they are not matching. So to calculate work done, I have to take that component of the force which is in the direction of displacement. So I'll break this up into two components. We have done this in an earlier video. It has two components, Fh, which is the horizontal component, Fv, the vertical component. So for calculation of work, I will use Fh into S, because that component is in the direction of force. As we discussed in an earlier video, Fh is equal to F cos theta into S, where theta is this particular angle. Theta is the angle between the force, that is the force and displacement. So this becomes the very general formula for work done, right? W is equal to F cos theta into S, or Fs cos theta, the way we want it. I hope this has given you some idea about what is work done and how we calculate work done, right? We'll look at a few cases now, right? And how work done varies with a change in angle theta. So the first case, right? We're looking at a few cases, right? First case, let us say when theta is equal to 0, that means the box, the direction of the force and the direction of displacement are same. Right? Theta is 0, this angle is 0, then both of them will in the same direction. In this case, work will be equal to F into S, because cos theta will be equal to 1. Cos theta becomes equal to 1, therefore work done will become Fs. Right? Case number 2 is when theta is equal to 90 degree. Right? In this case, cos 90 will become 0, therefore work will be equal to 0. No work is done. Now this is an interesting case. Let me take an example to explain this. That when the direction of the force, if I show it in a diagram, the direction of the force and the direction of displacement are perpendicular to each other. If this happens, then the work considered is 0. Let us take an example. Let us say this is a railway platform, and let us say this is a coolie, right, and he's carrying some luggage and he's moving in this particular direction. Right? Now as far as this luggage is concerned, right, the luggage is moving in this particular direction, whereas the force, the weight of this is acting in the downward direction. So you can very clearly see that the angle between the displacement and the direction of the force is 90 degrees. So in this case, work done is equal to 0. Of course, you have to very clearly specify work done by which force. The work done by the gravitational force is 0, because the direction of the gravitational force is downward, the direction of displacement is horizontal, angle is 90 degree, work done is 0. Okay? So this is an example of when angle is 90 degree. Okay. 3. When theta is equal to 180 degree. Right? So in this case, if I look at it as a diagram, the direction of the force would be, say, this, and the direction of displacement is this. So in this case, cos theta would be 180 degree, and therefore work done would be equal to minus F into S, because if this cos theta is cos 180 degree is minus 1. Cos 180 degree is minus 1. So this becomes minus Fs. Work done is equal to minus Fs. So in this case, we say negative work is done. Let me take an example and explain, right? For example, the work done by frictional force. If the object is moving in this particular direction, the frictional force acts opposite always, right? So this is the direction of the frictional force, this is the direction of displacement. So the work done by frictional force would be minus F into S. And from a concept point of view, that is also very easy to understand, that the work done by the frictional force will always be negative because it is trying to oppose the motion, right? So this is an example of work done. Right, so these are some of the examples that we have looked at, and I hope we have got now a clear idea about what is work done. So whenever we discuss work done, look at two things, in fact three things. Look at the force, look at the displacement, and look at the angle between the force and the displacement. And if you have knowledge about these three concepts, you'll be able to find out work done. Last point before we end the video, whenever you have a situation and you are asked what is the work done, you should first think of, or you should first ask a question, work done by which force, right? That becomes very important. For example, if this is a road and if there's a car moving on this, my drawing is not good, so generally I will not try to draw a car, but let us say this is a car, right, moving in this particular direction, and if you are asked what is the work done by the car, right, there's no answer to that question in that sense. What we need to specify is work done by which force, right? For example, if you look at the work done by the gravitational force is acting in the downward direction, displacement is in this direction, so work done by gravitational force would be 0. If you look at work done by frictional force, now frictional force is acting in this direction, so work done by frictional force would be minus Fs, because the displacement is in this direction and this. And if you try to find out the work done by the engine, right, now the engine is trying to push it in this direction, so the direction of the force and the direction of displacement is same, so work done by the engine would be F into S. So this is how we need to look at work done. We need to be very clear about which force are we considering when we are trying to find out work done. And if, as I said earlier, if we are clear about three things, force, displacement and theta, then we will be able to very clearly find out what is the work done and also very clearly understand what is the work done. Thank you. I'm doing this very short video on units of work. In the previous video, we understood what is work done and we got an equation for or formula for finding out work done. Work done denoted by W is Fs cos theta, right? Where theta is the angle between the force and the displacement, right? Now, if you try to understand or look at the units of work done, right, we can find it out from this particular formula. We know that the unit of force is Newton. The unit of S is meter, displacement is meter. Cos theta does not have any unit because it's a ratio. So the unit of work done would be Newton meter, right? This particular unit of this is the SI unit of work done, Newton meter, right? And 1 Newton meter, this particular unit, 1 Newton meter is considered as 1 joule, right? After the famous scientist, physicist James Joule, right? So work done unit is considered as 1 joule, and that is equal to 1 Newton meter. What is the meaning of this? What is the meaning of the word? What do I mean when I say 1 joule of work is done? The meaning is that if I apply a force of 1 Newton and that leads to a displacement of 1 meter, 1 joule of work is done, right? So if I have an object, whatever may be its mass, if I apply a force of 1 Newton to this particular object, and the result of this is that it gets displaced by 1 meter, then I'll say 1 joule work is done. This is the concept, this is the meaning of the word work done, 1 joule, right? This is the SI unit of work done. Let us look at the CGS unit of work done, right? So again, if I look at work is equal to Fs cos theta, right? The unit of force in CGS unit is dynes, is centimeter. So the unit would be dyne centimeter. That is the SI. That is the CGS unit of work done. Right? And this is known as 1 erg or 1 erg, right? That's the that's the CGS unit of work done. Finally, what we'll try to do is try and find out the relationship between 1 joule and work, this SI unit and the CGS unit, right? So if I write down 1 joule, that is equal to 1 Newton meter. Now we know 1 Newton is 10 raised to 5 dyne, and 1 meter is 10 raised to 2 centimeter. So that will give me 10 raised to 7 dyne centimeter, and we know dyne centimeter is erg, 10 raised to 7 erg. Right. Okay. So this is the relationship between the SI unit and the CGS unit of work done. 1 joule is equal to 10 raised to 7. Alright, we come to the end of this video. I just wanted to introduce you to the units of work done. Remember, the SI unit of work done, joule, and the CGS unit of work done is 1 erg. Thank you.